Lesson 29 is lenses, and although it's a long lesson, we can actually make it relatively short. The reason being, we've done all the legwork on lenses. Lenses is basically the opposite of mirrors. So everything we learned in mirrors applies to lenses, but there are just some things that are opposite. For example, in mirrors, we learned that a concave mirror is converging, while in lenses, a convex lens is converging. Before we get into that, let's just have a look at a quick video so you can see visually. I would demonstrate this to you live if we were in class. And so here's three light beams all traveling parallel to one another. Let's play the video. And the person is going to put a convex lens in front of it, and you'll see it has the purpose of converging the light rays. So those three light rays enter that lens, and then they converge at a single point. Now, obviously, this applies to your glasses, contact lenses, all kinds of application, microscopes, mirrors, magnifying glasses, not mirrors, magnifying glasses. This is all about converging and diverging lenses. And here we have a diverging. So this is a concave lens. And as you can see, it is making the rays diverge. But let's just go back to, he was doing a really good thing there. He was showing you that they're actually converging. Let me stop the video. He's showing you they're actually converging on the same side as the of the lens, or on that's actually going to be a virtual image, which we'll get to in a second. So let's go to our notes and lenses. The first thing you can do is kind of ignore most of this. What you need to know is this: a double convex. Double convex right here is a converging lens, and then the other one that we commonly do is this one here, a double concave, and that's a diverging lens. Okay, but let's just do some examples here before we even go on to the notes. Same as mirrors. So here's our principal axis. Let's start with a convex lens. So this is a convex lens. And for lenses, we're going to do focal points on each one. Some people call this F1, F2, F1 prime, F2 prime, don't really care. So this is the focal point, and we'll just call this F prime. And let's put an object here. There's our object. Now remember, this is a convex lens, and convex lenses are converging. And we're going to apply the rules that we learned in mirrors. So the first rule said that if you have a light ray that runs parallel to the principal axis, and for lenses, we're going to go to the center of the lens, then that ray will refract through the focal point. Okay. And the second one says, the second rule says if you have the one that goes through the focal point, now we're going to have to, I'm not going to do that one because I didn't draw my lens big enough. Let's do the center one. The center one, for lenses, often the parallel and the center ones are the best. And when we do ray diagrams for lenses, this is the center. We use this right here as the center. So all I'm going to do is take a light ray, go from the object right through the center, and that's where our image will be. I didn't draw that quite correctly. It shouldn't be on that second focal point, but that's okay. And what are the characteristics of this image? Lenses is that everything's the opposite. So since it's on the opposite side of the lens, that's where you expect to see it. Otherwise, when you put your glasses on, you wouldn't see anything. This is a real image. So it's opposite, whereas in mirrors, the real images are on the same side as the object. It's obviously inverted, it's upside down. And in this case, it's larger. Okay. Let's do another convex lens. Convex lens. And this time, let's put the object right here. So right here, so it's in between the lens and the focal point. Apply our rules, parallel to the focal point. Now, when you draw the one through the center here, obviously, you're going to see that these two rays are diverging. So this is where you're going to have to extrapolate each one. Extrapolate each one back. Oops, that was supposed to be green. Oh, well. Extrapolate this one back, and they're going to meet, that wasn't great. They're going to meet somewhere here. And in this case, whoops, in this case, you're going to get it's larger. It's right side up, so it's erect, and it's virtual because it's on the same side as the object. Again, the opposite of mirrors. So whenever you have to extrapolate the lines back through these dotted lines, then you get a virtual image. All right, and we'll do one more example. We'll just do a diverging lens. Diverging lens. Move further out. And we'll put the object there. Diverging lens to the center. Now this one's going to diverge, so it's going to go up in this direction. It's going to go up here. It's a diverging lens, but that's going to extrapolate back to the focal point. And the other rule that we can use is the center rule. Here's the center. Just draw a line straight through there. Because anything that goes through the center just goes straight, and there's our image. So this image is virtual, it's smaller, and it's upright or erect. Okay, so once you've done mirrors, you've done lenses. You just have to remember that things are generally backwards. Okay, and then your notes go through all these examples here. And so here's a good example of the second rule, which I didn't go through because I didn't draw my lens big enough. So here's the second rule right here. If it goes through the focus, as soon as it hits the middle of the lens there, then it reflects parallel. So there's a good example of the second rule. And here's a great example. Here's all three rules together for this lens right here, this convex converging lens. And then some examples of diverging lenses. So you can go through those. And is there an example? Here we go. Example right here. A converging lens has a focal length of, so it's converging, so the focal length is positive, of 0.22. If an object is placed 0.41 in front of the lens, determine the image will appear and identify its characteristics. So determine where it will appear. Let's draw a quick sketch of that. It's a converging lens, so therefore it's convex. Convex, focal point, focal. Has a focal length, so this is 0 from here to here is 0.22 meters. And from here to here is obviously 0.22 meters. If an object is placed 0.41, so where would that be? Well, this point over here will be 0.44. So 0.41 is going to be just in front of that. So if I put an object right there, determine where the image will appear in its characteristics. Okay, quick ray diagram. Am I being accurate here? Not quite. Hopefully you'll be a little more accurate with your placing these things here. So parallel to the focal point, and then right through the center, or let's do the other rule since we didn't do it last time. Through the focal point, parallel. And then if you draw one right through the center, actually that works quite well. If you draw one right through the center, very nice, sort of. And there's our image. Okay, now it's a pretty rough sketch. I'm not sure that I'm going to get the right answer, but it looks as though it's a little beyond this point. This point would be 0.44, so it looks like it's going to be a little beyond that. Let's do it algebraically. 1 over f equals 1 over DO plus 1 over DI. Exactly the same as mirrors. We're solving for DI. Plug in our numbers. Remember that if it's converging, then the focal length is positive. And solve for DI. Now, that one's a little hard to do with common denominators, so probably the best thing to do on that one is just get out your calculator and use it as fractions and just simplify this side first. So I'm going to go on the calculator. 1 divided by 0.22 in brackets minus brackets 1 divided by 0.41 and the brackets equals, and then I'm going to put it in fraction form. Oh my goodness grief. Okay. $950 over 451. Yep, that appears to be correct. Okay, and then solve for DI, so just cross multiply and divide. And so DI is going to just equal 451 divided by 950 equals 0.47, which seems quite reasonable. I said it was going to be just a little bit greater than that. 0.47 meters is the distance. And that is a real. It's real because it's on the other side of the lens. It is inverted. Is it larger or is it smaller? Well, based on the other diagram, we know that if the object is in between this point and this point, it should be larger. But let's just find out how much larger it is. So I have my DI now as being 0.47. I have my DO as being 0.44. Let's find out the magnification. The original question did not give me the height of the initial object, did it? No, it didn't. So let's just find out my magnification. My magnification equals negative DI over DO, which equals negative 0.47 divided by negative 0.44. Oh, not 44. Sorry, I made a mistake here, and there's no way I'm redoing this whole video for that little mistake. It's 41. 41. Divide those, and you get 0.47 divided by 0.41 equals 1.14. Negative, and the negative just indicates that it's upside down. Negative 1.14, which means it's larger, slightly larger, and upside down, or inverted. Okay, so that's it, and that's really it for lenses. Recommend that you go onto YouTube once again, and there's some really good videos on the lenses. We'll see you for polarization, which is the last lesson of EMR. Oh no, we've got 2 more lessons, diffraction and then polarization. Diffraction is super cool. You're gonna love it. Bye.